Okay, so before we start, just a review of last class. So do you remember what we discussed in the last class? Main topics that we discussed in the last class. We basically discussed the need for I/O, the importance of I/O, and next, I mean, because I/O is needed because you finally communicate with humans. So that's the need for I/O. But more than I/O, we discussed about other things also. So what is the main thing that we discussed about, which is related to the I/O? Anybody? No? Okay, so we discussed about the concept of bus. Okay, how bus is important for connecting your I/Os to your processor. Okay, so you typically have uh, processor memory bus, okay, which is proprietary, and then you have bus which using which you connect the I/Os to the processor. So that is basically that is a standard. You have standards, many types of standards for connecting I/Os. So bus again should have certain properties. It should be able to support wide variety of devices with different speeds and so on. Okay, so that also we saw, and then we talked about bus arbitration because you'll be connecting many devices. So if multiple devices request for processor access at the same time, if multiple IOs want to send the data or want to receive the data from the processor at the same time, then you have to arbitrate between the different IO devices. So that's where the bus arbitration schemes came into picture. So there are different types of bus arbitration schemes. So the basic ones that we discussed are daisy chain, and then the other one we discussed was centralized based architecture. Okay, centralized arbitration, and then we a particular modifications of those centralized uh, architectures we also talked about, where the devices itself will take care of the control on who gets access. So that is more like the decision will be taken at the device end. Okay, so that is one more types of arbitration scheme that we saw. Okay, so these are some of the things that we saw in the last class. And again, I asked you to go through the topics related to the storage. Okay. So today we'll just briefly discuss about the multi-core architectures. What exactly do you mean by multi-core, and what are the things that you have to take care when you have a multi-core architecture? So that's the main topic for today. So till now, as I said, we discussed initially about the processor implementation where you have a register file, ALU, you have different processing steps, different steps of execution that will be there. Okay, so you have instruction fetch, decode, and so on. But we also discussed about how this processor is connected to different IOs. Okay, so you may be having a monitor, you may be having a keyboard, you may be having a secondary disk. Okay, so we talk about. Do you remember what we call this in the Intel processors? What do they call this bridge or bus which is connecting your processor and your main memory? Do you remember what we called this, or what Intel usually calls this as? So this is your north bridge, and this connection is basically your south bridge. And again, your this bus and this bus is again connected to some other architecture. So some other bus based architecture. Okay, so this is your south bridge where IO devices are connected. This is your north bridge where your main memory is connected. Okay, so that is Intel specific. But again, you should know that there is a bus which will connect your processor and your main memory, and then there is a bus which connects your IO, and then there is a intermediary bus which connects your north bridge, or this particular bus and this particular bus. Okay, so there are many characteristics that also we talked about last time. Okay, so you have your bus should support different speeds because these are very have a low speeds. These will have high speeds because it is interacting with a machine. Here it is interacting with a human, so it will have low speeds here and high speeds here. So all of those speeds you should be able to support, and it should be able to support many such devices also. Since many of the devices are connected to the same bus, you need a bus arbiter which will decide who gets access to the bus finally, and all of those things we have discussed. So this is like a single core computer. Now, when you say a multi-core computer or multi-core architecture, what they do is they just replicate the processor. Okay, So you have one core here, second core, third core, and fourth core. So the basic execution stages, they just replicate 4 times. And then you have a bus interface, which will interact with main memory or which will interact with your IO bus using a similar architecture. Only thing is you have multiple cores where you will be able to fetch multiple instructions and execute multiple instructions at the same time. Do you know what this is similar to? So you have multiple cores, no? So yeah, it's like you are replicating the stages. So this is similar to what architecture that we have discussed already. This is similar to what architecture or what kind of multiple issue. It's very similar to multiple issue. Okay, but the major thing there here in that is you still treat it as a single core, although you'll be able to execute multiple instructions at the same time. You still have to follow certain things there. So you have to make sure that the instructions are executed in order. Okay, so you have to write into the register in order. So the register file is same for all of, even though you replicate many blocks there, like ALUs and functional units, the register file is the same. Okay, so everything changes in that register file only. But here you have a separate register file. So these are independent processors that are available with you. And this is used for parallel execution. So there you do instruction level parallelism. Okay, in the case of multiple issue processors, we call it as a parallelism, but it's an instruction level parallelism. Whereas when you have multiple cores, you will be implementing something called as thread level parallelism. Okay, so thread level parallelism meaning all of these cores will be executing different programs at the same time, might be executing different programs at the same time. In the case of multiple issue processors, you will be executing only one program at a time. Within that one program, within that program is basically divided into threads, and within that threads, you will be executing a sequence of instructions. So you'll not be executing a different thread, you'll be executing the same thread. But here, all of these cores can be executing altogether different threads of the same program or different threads of a different program altogether. So that's the difference between multiple issue processors and multi-core processors. Okay, so you should try to understand the difference. So here also we are replicating, but here we are replicating the entire processor, not just few functional units. Okay, we don't have just two adders or two multipliers, or we don't give additional units. We are replicating the entire processor itself here. Okay? And each of the processor can work independently. So threads run in parallel here. So that is why this we call it as thread level parallelism. Okay. So OS perceives each core as a separate processor. So there it will treat it multiple issue processor as still single processor. Only thing is you'll be able to fetch two instructions at the same time. That's the only difference. But here it will treat, OS will treat all of these four cores as individual separate processors, and there will be a scheduler which will map threads onto the core. So if there is a thread available that needs some execution, and if there is a core available that is free, then that particular thread will be scheduled onto one of the free cores, and then the execution will happen. Okay. So we have to understand whenever we talk about thread. Okay, so we ought to understand that there is something called as simultaneous multi-threading. Okay, so this is very similar to your multiple issue. Okay, so this is very similar to your multiple issue processors. So what happens here is you still have a single core. This is still single core processor. Only thing is you have multiple functional units. So simultaneous multi-threading processor is another variant or another name for a multiple issue processor where you have different functional units. And suppose you only thing is you will be able to execute instructions from different thread here. So suppose there is an integer operation coming that can be executed on an integer functional unit. And if there is another thread which requires a floating point operation, and if you have a floating point unit available which is free, then you can execute instructions from that thread. So simultaneously, you will be able to execute two threads. So that is why this is called as simultaneous multi-threading, but it is still a single core. Okay, this is not multi-core. Okay, it's still a single core because the main processor is still single. Only thing is it is making use of two different functional units to execute instructions from two different threads. Okay, so that is what we call it as simultaneous multi-threading in a single core processor. Okay, but simultaneous multi-threading processor will have limitation. For example, if you want to execute instructions from two threads which will require integer functional unit, that you will not be able to do. Okay, so this puts a limitation. So this scenario is impossible with a, single simultaneous multi-threading processor, which is equivalent to a single core. So when you have multi-core processors, then you will be able to execute two different threads, which will require integer function units because you have two different function units which are available to you. Okay, so this is the basic idea of multi-core. So generally, multi-core processors can be categorized into two things. So one is called as SIMD, which is single instruction multiple data. Okay, so you'll have multiple cores, but on all the cores, you'll be executing a single instruction. Okay, but you will be operating that instruction on different data sets. Okay, so this is effective in a certain kind of application, specifically image processing or vector-based applications where you want to do operations, like you want to add a array. There will be many elements in an array. Let's say there are 4 elements, and there is another array which is having 4 elements. And if you want to add such that this element gets added to this element and gets stored in the first location, this element gets added to second element and stored in second location, so on. So here the operation being done is same, but the data that you are operating is different. Okay, so that is basically an idea of single instruction multiple data. So can you tell me in which applications do you see this kind of operations? Which kind of applications do you see these kind of operations where you operate on individual elements and then get an individual result, and similar operation you replicate or you do it on other elements also? So generally they call it as vector, okay, vector operations. But again, vector, if you take a 2x2 vector, then that becomes your image. Okay, so it's basically in image processing applications. Again, matrix is basically an image. Okay, so it's matrix operations or image processing based operations, both mean the same here. So that is where you use this kind of processors, where you still have multiple cores, but all of the cores will be executing a single type of instruction, but they'll be operating on different data sets. Okay, so that example is for graphics processors. And you have another case, another variety of multi-core processors, which is called as MIMD, where we call it as multiple instruction and multiple data. Okay, so it basically means that there are multiple cores, but all of these cores will be executing different instructions, and they'll be operating on different data. Okay, so if this is these are the two examples of multi-core, there is another variation, right? So you can always say I have single instruction single data or single instruction multiple data. So can you give me an example for these? Where are these used? Single instruction single data and single instruction multiple data. Sorry, not single instruction multiple data. What is it? Multiple instruction single data, MISD. Okay, so MISD is one possibility, right? Because we are talking about instruction and we are talking about data. Same instruction multiple data is used in graphics processors. Different instructions on different data is generally whatever you call your general purpose multiprocessors are basically coming under this category. So you have Intel quad core processors or your processors that sit in your mobile phone. So all of them come under this category, and the GPUs come under this category. And if you're talking about instruction and data, there is another variants also. So you can operate single instruction on single data at a time, or you can do multiple instructions, but there will be a single data that you operate on. Do you know any examples for these two? So what will be this? I think this is simple enough. Single instruction, single data. What do you mean by it? So there will be a single one instruction at a time that will be executing, and it will be operating on a single data. So what is an example for SISD type of processors? Any idea? A single core processor. Till now, whatever we have been, and it will be operating on a single data. It will not be operating on the same data. So it's like a single core processor. Okay. Any example of this MISD, multiple instructions operating on a single data? You know any processors which come under this category? I don't think any like not many commercial processors or not many processors that we may know of come under this category. Maybe a specific case where you operate on a single data, use multiple instructions to manipulate that, that can come under this category, but this is generally not used in many of the applications. But these three are mostly used in many of the different applications. Okay, so this is about classification of multi-core. So again, there is another classification with respect to memory. So there is one classification based on shared memory. So in this model, there is one large common shared memory for all of the processors. Okay, so this is called a shared memory model. And then there is distributed memory model. In this model, each processor has its own local memory, and its content is not replicated anywhere. But most of the multi-core processors use a combination of these. Okay, meaning some part of the memory will be shared, and some part of the memory will be private. Okay. So again, distributed memory model is slightly different, which will not talk about. But even in this case of shared memory, we still have each processor having its own private memory. Okay. So most of the memories, multi-core chips, what do they have is they usually have a cache which is private, and then you have a level 1 cache, and you might have a L2 cache which is either private or it is shared, and then you have your main memory. Okay, so this is some examples that I will give for different kinds of architectures with respect to memory hierarchy for multi-core processors. Okay, so there are three scenarios here. So in the first scenario, you have two cores. Okay, so both have a L1 as the private cache. Okay, but L2 cache is shared. Okay, so this L2 cache is shared among both the cores, and then you have main memory which is shared. In another category, you have L1 and L1 cache to be private, L2 cache also to be private, and then you have a main memory which is shared. So this is for your AMD Athlon and Intel Pentium type of processors. And then you have another scenario where you have three levels of cache, all three are private, and then you have a common memory which is your main memory. So by seeing this, can you make some general statements? So by seeing these three architectures, these are three different types, but can you make a general statement based on these different types of architectures? So what can you say about L1 cache? And what can you say about your main memory? So main memory is always shared. Okay, so because you'll have only one RAM cell. Okay, so main memory will be always be shared among all the cores. Okay, so this is first statement. The second statement I can say with this is you have L1 to be always private. Okay, L1 will always be private. Okay, and then if you have L2 and L3, they can either be shared or private, depending upon the architecture, depending upon what exactly you need. So here you have shared or private. Okay, so you can at the max, most of the processors have maybe two levels or at the max three levels. Okay, so we'll not have more than three levels in any of the processors, and we don't have any processor without the cache also. Okay, so there will always be a cache. L1 cache will always be private. If you have multi-core processor, if you're talking about multi-core processor, and main memory is always shared. In between, you have different levels of memory, which is either shared or private. Okay, so that depends on the different architectures. So when you have multiple cores which have a separate private cache, can you tell me what problems could arise? You have a L1 cache and L1 cache here. So can you tell me what could be the problems if I have a private cache? What problems might come? Any ideas? Any guesses? Inconsistency. Can you tell me an example? What do you mean by inconsistency? Okay, so let me give some idea about that here. Okay, so let's say you have, okay, so let's say you have 30 caches The value is updated in one cache and not in the main memory. Okay. Okay. So let me give an example. Let's say there is some location x which sits in the main memory and x is 4. Okay. Now the core one requests a read to x location. So it might be a mess initially. Eventually, x will be placed in the cache. So the value of that location, the data in that location will be 4. And then let's say this core also requests for the same data. Okay, and now let's say x is equal to 4 here. Now you have x is equal to 4 in the main memory, x is equal to 4 in the L1 cache of core 1, x is equal to 4 in the L1 cache of core 0. Now suppose, okay, so suppose there is a write operation initiated on core 1. Okay, so that changes the value. Okay, so let's assume it is following a write back scheme. So it will not update immediately. So x value, let's say it is changed to 5. So can you tell me what is the problem in this scenario? What's the problem in this scenario? So now at this time, let's say the core 0 will request a read on x. Now suppose even if it is not there initially in L1, let's say if I say read x now, what value will be read by core 0? What value will be read by core 0? So it will see a miss. When it sees a miss, it goes to main memory to access the data. In the main memory, you still have x is equal to 4. Okay, so you see that there is same location. Sorry. So there is same location with different values. Okay, so here x is the same location with a value of 5, but here x is this location which is having a value of 4. Okay, so this is called as cache inconsistency in the memory. We also have, and again, if you're talking about x being here also and x is 4 initially, so this cache has a different value and this cache has a different value for the same mapped location. X is the location that is mapped, but for the same location you have different values. So this is basically inconsistency, or in the multi-core, in the normal terminology that they use is called as cache coherence problem. Okay, so all caches should be coherent, meaning any particular location gets changed in one cache, the same should be reflected on all the caches if that particular address is there. So if there is an x address in 3 caches, L1 of core 0, L1 of core 1, okay, and L1 of core 2. So if this has x is equal to 4 initially, x is equal to 4 initially, x is equal to 4, then if this writes 5, now these two should not read x as 4. Okay, so they either should get the value, updated value, and place it here, or they should invalidate these data. Okay, what do you mean by invalidate? You make the valid bit to be 0. So, and when you make your valid bit is 0, and also this value should be updated in the main memory. And when you make valid bit 0, whenever you request for a cache location, it will go to the main memory and then fetches the correct data. Okay, so that is what we call as cache coherence. You have to make sure that all the caches are coherent. Okay, so if you don't do that, then it will cause a problem. Since we have private caches, how to keep the data consistent across all caches is one question. Each core basically should perceive the memory as a continuous array. It should not see that the memories are divided and they are private. Okay, so they should think that the entire memory is available for each of the cores that is available. Okay, each of the cores that are there. Okay, hence you have to solve this problem somehow. Okay, so there are many algorithms which have been designed to handle this problem, which basically sits in the cache controller, which will take care of updating the caches and making sure that there is consistency. We'll just see one example related to it and maybe one basic protocol. This is again very fundamental protocol. A lot of advanced protocols are also there. Okay? So again, I'll talk about the same case. So you have let's say X memory address having this value, and let's say core 1 reads X and then core 2 also reads X value. Now in the second case, let's say if core 1 writes X into X a new value, okay, let's say 21660. What happens is the X here and the X here are not correct. Okay, only the X here that is having the recently updated value is correct. Okay, So if you assume, even if you assume that you have a write through scheme, and let's assume you update to the main memory, even in that case, what happens is you see that the core 2, if it tries to read from X location, it will get a stale copy, meaning it will get a wrong copy of that location. Okay, so this is not correct. Okay, so you have to come up with some algorithm. One solution is invalidate based protocol with snooping. Okay, what you do is at the bus, you constantly keep on checking what memory locations are accessed, okay, by the processor, and what memory locations are updated. So based on that, you invalidate some of the locations. Okay, so that is called as invalidation. If a core writes to a data item, all other copies of this data item in other caches are invalidated. Okay, so let me give an example for that. Okay, so that is achieved by snooping. So all cores continuously snoop the bus which are connected to the cores. Okay, so this is like a bus which is connected to all of the caches. You constantly keep checking on this bus what activity is going on. Okay, now let us take the same scenario. So core 1 and core 2 have both read X. Now let's say core 1 writes into X a new value. So whenever this new value is written, so it sends a invalidation request. So what it will say is, whoever is having the value, this location X with you, you invalidate it because I have recently updated the value and whatever value you have is wrong. So that is why you put a valid bit as 0 for your locations wherever you have mapped it to X. Okay, so that way you can send an invalidate request on the bus. So wherever that location is found, the valid signal will become 0. Invalidate is not like deleting the entire value. You just make valid bit of the corresponding cache block as 0. So that way, this core, whenever it tries to read, it will see a miss. It will not see a hit, and it will go and try to fetch the value from the main memory. Okay, but the thing here is you have to compulsorily follow a write through scheme. Now, what happens if it is following write back scheme and if it is not updated? Then also it will create a problem. Okay, then it's the responsibility of this. Okay, it's the responsibility of this cache. Whenever this cache sees that a particular location might be available in multiple caches, whenever this cache updates the value, even though write back scheme is followed, it forcefully writes the data into the main memory. This is very similar to what we have seen in the last class. So whenever we saw that IO was requesting a read or a write on a data, and that data was updated in the cache, you did forcefully write back into the main memory. Right? Similar thing here. Okay, so but how do I know that the location X is shared? So for that, you have some additional bits which will tell you if that particular location is shared, or if that particular location is only private, or is it only there in the core 1. So all of that information will be required. Okay, so a simple technique, if you are assuming write through scheme, is to send an invalidate signal so that all the other caches which will have this location, they will just put valid bit as 0 for the corresponding mapping. Okay, so this is one method. And after invalidation, core 1 reads, the cache miss will occur and it will load a new copy from your main. Okay, so the second one, an alternative to invalidation protocol, is called as update protocol. So what the core 1 does here is, so the core 1, when it writes a new value into the X, it earlier it used to send the invalidate signal. Now it will send the location along with it the updated value. Okay, along with it the updated value also will be sent. So when it sends the updated value, the other other caches which will be checking this particular bus, they'll see that X is changed, and they'll also see the updated value. That value will be loaded into the corresponding locations. And whenever you see a read here, it will not be a miss, it will be a hit, but it will read the correct value. It will not read the wrong one. What is the disadvantage of this case? What is the disadvantage in this scenario? What will be the problem if most of the multi-core processors do not follow update protocol? Okay, why do you think that is? It's not about being private anymore. Again, it's not that see, private meaning, when I say private, this cache is accessible by this core only. That's what I meant by private. But I'm not saying that the data is private to this to a particular core. Okay, the data can be available in multiple caches at the same time. Okay, so that's not the right answer. Anybody? Why is update not stall due to writing? But this need not stall, right? This code need not stall. It can send the information and you can start executing other things. Read write race conditions. Okay, that might be one issue. The other issue is again you need to have a complicated bus here because it's not just invalidate signal that you are sending. Invalidate is just one bit information. It's just address and then one bit. But here you are supposed to send the data as well, the data that gets updated. Okay, so here a bus implementation will be a little more complex. Okay, so that's like one of the disadvantages of update protocol. But most of the processors use invalidate protocol. But again, they use not just a simple invalidate protocol. They use sophisticated protocols that will be available. In this case, write through may not be required. Yeah. So whenever it is getting updated, whenever sending information, it's you can as well send that information to this main memory also. Okay. So that way, whether you want to implement it as write through or write back, uh, it's either way, it's fine. Okay. Yeah. Okay, so this was a very basic protocol. Okay, so there are more sophisticated protocols that are available, which use some extra states to indicate whether you have whether you have whether the particular location is shared among caches or whether it is present in only one cache. Okay, so all of that can be modified. So there are some protocols like MSI, MISI, MOESI, MOSI. So there are many protocols. So here the protocol name tells you about the different states that are available. Okay. So M stands for modified, S stands for shared, I stands for invalidate. And again, in updated protocol, they have added one more state, which is exclusive. Modified basically means this is indication that a particular core has modified the data. Okay, so that information has to be sent. And shared is like whenever a particular read is done, it is assumed that the data might be shared with others. Okay, so when it writes into that location, it gets into modified state, and it might be sometimes only present in a single cache. That means it is exclusive. So whenever you have an exclusive location, so whenever you write into it, you don't have to broadcast anything, okay, because it's exclusive only to that particular cache. So that way you have many states that will be indicated as part of the cache blocks. So now you have to imagine that in the cache block, there is not just the data. So there will be a tag, there will be a dirty bit, okay, there will be a valid bit, and in addition to that, there will be a state bit which will indicate one of these possible states. So based on that, it will make a decision on whether to update the data, whether to treat the data as valid, invalid. Okay, so all of that will be done based on this particular state that might be stored. Okay, so I'll not get into the details. The details will require more explanation of the protocol. But again, that I'll not be discussing at this point. Okay. I think that's all from my side today. Okay, so I think that's basically sums up the course, what I wanted to cover as part of this course. Again, there are additional topics, advanced topics that are available that will not be part of your examination syllabus. I'll share some video lectures of that. If somebody is interested, they can go through some advanced topics like in dynamic multiple issue processor or dynamic scheduled processors. I talked about algorithms being available, right? Uh, you have scoreboarding technique, you have you have Tomoslo's approach. So those are some of the algorithms. Yeah, you have register reorder as a case of making sure that the write happens in order. So all of those things have explained there. Again, this is not that will not be part of computer architecture syllabus. But if somebody is interested to go through some advanced topics, I'll share the videos of that. You can go through. Okay, I've also talked about this there. Okay, so more details. I've given explained a state diagram of a simple protocol that is this. Okay, so MISI protocol also I've explained in one of those videos where you'll understand how exactly this cache will change their states according to the read or write operation that will happen. Okay, so all those advanced lectures are available. I'll share those videos in the same folder. If somebody is interested to go through them, they can go through. Okay, but as part of this computer architecture course, I think we have reached the end of the syllabus. So we still are left with three lectures, I guess. Okay. So one is Wednesday is a holiday, then we have Friday's lecture, and then Monday and Wednesday. Okay, so that is 23, 26, 28. I'm planning for an invited talk. I'm not sure whether it will materialize or not. Okay. If not, what do you want me to do in those lectures? Don't tell me more problems because we already have more problems that are available with you as part of question papers and things like that. If even more problems you require, I don't know from where to bring in. But again, let me know what you want me to do in the next three lectures, or you want me to finish off and then leave you guys free. Any suggestions or anything? Okay, career placement guidance that I can do. Okay. Okay. So I can give you general guidance also. So probably that we can discuss next lecture. What about the other two lectures? Maybe one lecture we'll keep it for guest or invited talk. That I'll see. I will still have to contact. Normally, I used to arrange this talk with your seniors, but last time I could not do it, and this time I don't know whether I'll be able to do it or not. I'll try. Okay, so that will be for one lecture, and one lecture I'll give you general guidance. I used to take this last lecture also, where I used to give some philosophical or life lessons. But again, last semester, last year, we were in a different scenario, so that's why I did not do that. Maybe if somebody want, I can do that also as part of your career placement guidance. Anything else? So this basically concludes the computer architecture syllabus for your examination at least, or for this as part of this course at least. Of course, computer architecture still involves a lot of things. So for that, a few video lectures I'll upload, which you can go to. Okay. One more thing I wanted to announce. This is for all students. I think you might have got a mail already for the feedback. Okay, so I think from 13th to 25th is when you're supposed to submit your feedback for the course in the link provided by UGSD. So please do it. Okay, for both the lab sessions as well as the lecture sessions. Okay. Yeah. Anything else? Any doubts you have related to any of the topics that I discussed? Any inputs you have regarding the course to make it better? What did you like? What did you dislike about the course? Okay, let me end the recording. Some people might be shy. Okay, so that's all from my side. Okay, for those who are seeing this video, I'll just stop the recording.